Hello, and welcome to the first lecture of our unit on energy. In this lecture, we're going to review what you guys did in the spring lab. And if you recall, in the spring lab, you analyzed a graph. Now, that graph had force on the y-axis, and it had stretch on the x-axis. And the shape of our graph was a straight line whose y-intercept was not at 0, 0. Now, the first thing we want to talk about is what is the meaning of that y-intercept? Well, the y-intercept corresponds to the loading force of the spring. The loading force is the minimum force necessary to stretch a spring. Now, there are two things that you should know about loading forces. Thing number one is that all springs in the real world have a loading force. Oops. You always have to apply some kind of minimum force in a real-world spring in order to make it stretch. Now, of course, this is an introductory physics class, and we don't tend to enjoy dealing with the real world. Instead, we like to idealize things, and ideal springs have no loading force. And that is typically what you are going to be seeing in practice problems. Unless they specifically tell you what the loading force is, we tend to assume that this is just going to be an ideal spring, and the slope, or sorry, the loading force of that spring is going to be 0. The next part of the graph that we looked at, right, is we always look at the slope. And so the slope of our force versus stretch graph in this lab corresponded to the spring constant. That spring constant describes the, quote, stretchiness of the spring. Now, what do I mean by stretchiness of the spring? I'm saying, is it easy to stretch? Is it hard to stretch? Now, spring constant, we have a variable. That way we don't have to write out the words spring constant every single time. And that variable is going to be a lowercase letter k. So in any practice problems, if you see a number with a k, you know that that's trying to tell you what the spring constant is. The unit is newtons per meter. And this is also helpful for you to know, because if you're given some kind of value with a unit of newtons per meter, you know that they are trying to describe to you that spring constant. Now, if your spring constant is quite small, that's trying to tell you that this spring is easy to stretch. If your spring constant is quite large, well, that's trying to tell you that this spring is hard to stretch, right? It takes a lot of newtons in order to get that same stretch compared to maybe something with a low spring constant. The last piece that we looked at is we looked at the area of this graph, and remember, the area means going from your line to the x-axis. And the area of a force versus stretch graph tells us about the energy stored in the spring. So what is energy? Well, we don't have a really precise definition for it. It's this weird quantity that we know exists, and we know that we can pass it from one thing to another thing, but energy is invisible. And we can't touch it, so we just have a somewhat vague definition for energy. It is the ability to cause change. Okay, now the variable for energy, so that we don't have to write out the word energy every single time, is a capital E, and the unit for energy is the joule. Here, that's how you spell the entire thing, but most of the time we just use a capital letter J to represent joules.